Okay, hello everyone. I hope you had a great day so far. We are going to continue today our discussion about the inverters topology and how we could on the model for the switching and how we could control that switching with the PWM technology that we mentioned is one of the main kind of like components of the inverters configurations. But before I start continuing our discussion, is there any question from the previous session? Go ahead.
So we talked about multi-level inverters. What are they like used for? Like what are they in?
Multi-level inverters, the advantage that they bring us is that they would give us less distortion at the output, so we have less harmonic at the output, and it would give us the more capacity for delivering power, okay, to our whatever application we have. Okay, so because of the less voltage stress that the switches has in a multi-level inverters, we could go up on a voltage generally. Okay, so each level would face lower voltage stress, but the whole multi-level would have higher voltage level compared to the single or like regular configuration of the inverter. So that way we could uh, provide more power because current is constant, more voltage, more power. Okay, so something like that. Now, where it would be the application of that when you have a high power demand. Okay, like most of the high power. When I say high power, I mean industrial kind of like scale, not a household scale. Household scale, not high power. Okay, so in a high power demand, like in a transmission in a grid or like an industrial scale, multi-level is more kind of like has a better kind of like characteristics, and it's more popular for uh, being kind of like adopted for the configuration. Okay, so this is one way of like we could like decide between the normal like single phase, single level, or like kind of like a full bridge versus multi-level. Another way is that the fact that it would reduce the harmonics significantly. Okay, so if you have any kind of like application, that distortion would kind of like affect your work, like for example, like in very sensitive kind of like actuators, like in surgeries, like those kind of like actuators or like those machine or motors that the surgeons use for the surgeries. They have to have a certain level of accuracy. Therefore, distortion of the voltage could affect the accuracy of the work of those machines or any kind of application. Even like sometimes in a very high sensitive computers or servers or like the IT kind of like application, when the device is very sensitive to the distortion, okay, then it goes without saying that we have to move on toward multi-level. Why multi-level and not adding some filter? Because another way, like the oldest way to reduce the distortion is to add filters. Because those distortions are harmonic, are high frequency component that we don't want, or low frequency component that we don't want. Okay, other than our desired frequency. Okay. The old way is to add filters, but filters are not cheap, especially when you go toward like a high power, or you want to have a very narrow band pass filter, like very an extreme narrow band pass. You want to like have exactly like a very tiny window of frequency to be passed to your actuators, and all the others gonna get filtered. That's not easy, and it's not cheap to do. Okay, so another way is to just use multi-level that by its configuration and by like inherently would reduce significantly the harmonics, okay? And then a simple filter would do the rest, deal with the rest. Okay, so did I answer your question? Okay. Any other question about previous session? No? Okay, before I start, I already uploaded this PPT. I don't know if you checked the Canvas or not. I uploaded this PPT, and I'm continually like upload the video record of our sessions, so you can have access or review the concept if you miss anything or you want to like review anything. I'm gonna post them on Canvas, so check regularly the Canvas, and I'm gonna add starting from probably next week. I'm gonna start uh, adding some videos on details because like in lecture we have a limited time, so I have to like just pinpoint to main concept, and I only explain to the details of the very important one. The rest of the details that I cannot cover in the lectures in the class, I'm gonna make some videos and I'm gonna upload them. So if you want to like learn more about those concepts, check out those videos, okay? Plus, as I said in the first session, I'm gonna do all the assignment through the semester with you, okay? So when I'm doing those assignments, I'm gonna record myself doing that, either the simulation or the hardware, okay? And I'm gonna put it on Canvas. So it makes your life much easier when you want to do the assignment. So check out the Canvas regularly, okay? So any comment or concern or question? No? Let's continue our discussion about the inverters topology. Now, last thing that we talked about in previous session was the model that we could have, the mathematical model that we could have for a simple half-bridge inverter, okay, when it works to deliver power to our AC system. And we run a KVL over our circuit, if you remember, and we come up with this differential equation, okay, based on the KVL that we had in our equivalent circuit model that we developed. You remember that? So that was the last point that we had in our previous session. We said, okay, we had our differential equation driven from a KVL, which describes the dynamics that happening in our system. Okay, remember what we talked about? One of the most important analysis that we do for any kind of system is the dynamic analysis. Okay, what happens if anything change? Now, for example, in here, our variable is current. Okay, what happens if the current change? That differential equation would gives you the answer. Okay, that what would be the effect of any type of change in the current. Now, the parenthesis. Current could normally is and could represent the load. So this differential equation basically gives you the load dynamic, the behavior of inverters toward the load dynamic. Make sense? So that's very easy. It was a one loop KVL, but see how much information we could get out of it. Okay, so I want you to like develop this kind of thinking. Okay, so please pay attention to those kind of like what that means. Like, okay, why I is the function, why input, why, you know what I'm saying? So this ask yourself this question or ask me those questions if you want. Okay, so now instead of directly solving these varying kind of like variables, putting in varying variables with alternations, we wanted to like take advantage of a certain kind of like techniques named average model, okay, to simplify our mathematical calculation. How we could do that? Now, as you see, and as we discussed previously, our voltage that we have, okay, based on the inspiration that we had from Fourier series, we could have described those voltage with three type of kind of like component: a DC component or offset. Okay, the main component, which was that h equal to 1, okay, and the rest of the frequencies, which was our distortion, that we call it harmonics. Okay, that was the three main component that Fourier series would give us if we apply that to our waveform, to that arbitrary time variant waveform. Okay, now if we input that waveform into our system, into our formula, into our KVL, okay, we could develop an average model by separating, okay, the constant, whatever we could take an average and kind of like represent it with a constant value, plus the distortion. Some kind of superposition kind of like effect, okay? Like for example, if our current is time varying, okay, we could divide those three components, okay, into the components, the average of those three components, okay, plus the variation of those three components. Now, I want you to be careful about that. It's not like, because before we had the main component, the DC component, plus the fundamental, plus all the harmonics, okay, f of h, for example, okay? It doesn't mean that, like, for example, this one is exactly contributing to this one, and this one is only contributing to the alternating part. No, all of the three components contributing to both parts of our averageable part of a signal and the variation part of signal. Is that make sense? Any question about that? We are not dividing those three components to two groups. Those three all together would create a waveform, and all the three components would contribute to an average voltage and some variation. Are we good? That's very important, okay? And when I say it seems easy, but I could guarantee you most of the people doesn't consider that. Okay, so please be aware of that. Now, if we are able to do that, now we could separate using that superposition kind of like principle, right? Okay, we could separate our average signals from our variation signals. So we run 1 kVL over our average signals, okay, and 1 kVL over that variation signals. See? 1 kVL over the average one, 1 kVL over the variation one. And then we could have a simpler kind of like model for averaging those. Why? Because if the average, the variations, that omega s is large enough, the fundamental frequency is large enough, that means those variation are very, very low, so we could neglect them, and we could get rid of the second KVL, which normally is. So if in our system, the natural frequency is lower than the fundamental frequency, which is normally the case in power system, okay, we could neglect the second category and only consider the average part and simplify our model. Any question about that? No? Consider this. You have a natural frequency in your system, okay? And you input a signal with a certain frequency and their harmonics into that system. The harmonics are higher than that fundamental. Okay, there are multiple integer of that fundamental. Okay, so now if your fundamental frequency, sorry, if the natural frequency of your system, okay, is much lower than your fundamental frequency, the lowest input frequency, okay, then you won't see any resonance in your system. Is that clear to physics? Okay, so now, if you don't have any resonance, that means those variation would not increase or create a significant. Eventually, they would decay and disperse through the system. So we could ignore them. They're just gonna dissipate through the system. If they would have make a resonancy, that would be different because then they would have like a huge effect on our dynamic. But since they are much far from the margin of resonancy in our system, so they are safe to ignore. So if it's safe to ignore, why bother to do the math? Let's get rid of it. We only follow the average part, which is the major part. Did I answer your question?
Yeah, thank you.
Okay. Now, if we do the average part, okay, knowing that the average, you said the function that we had, the time variant function that we had, the aspect of the time variant always came from those S function, the switching function. Do you remember that? Because our voltage was DC and the current was DC, okay, at the source. What it would change from a constant to a time variant was the effect of the switches, which we define them based on the time function of S1 and S4 for switch, top switch and bottom switch. Do you remember that? Okay, so now if we want to average those voltages and currents, basically what we're doing is averaging those S functions because they are the one that we are averaging over. Make sense? The rest is a constant multiplication, a constant coefficient. Are we good? Any question about that? That was the, let me go back. This is the voltage function. This part is constant number. This part is constant number. If you want to average, you average the time variant function, which is S1 and S4. Same goes for the current, okay? Now, we know we define the duty. If you remember, we defined the parameters named duty cycle that we said the portion of the time in one cycle that the top switch is on, we call it D, okay? And we call it the duty cycle for the half bridge. Do you remember that, the definition? Now, if this is the TS and this is the duty cycle, which means DTS, and the amplitude of the pulse is 1, what would be the average of the S1? It's simply, if you do the integral, it's simply the D. Correct? Are we good on that? It's a portion of D. If you do the per unit, it's D. And because the bottom switch was on, whenever the top switch is off, that means, okay, the average switch should be the complement of the switch of the bottom one, should be the complement of the top one. Are we good on that? So the average of S1 is going to be D, or duty cycle. So the average of S4 is the complement of the S1, which is 1 minus D. Are we good? Any question about that? Now let's put it in the formula that we had. You see the formula before? When we had S1 and S4 in the voltage of the terminal, now the average becomes the same times that S1 minus S4, which if you do that, it becomes 2D minus 1. You remember VT originally was VDC time S1 minus S4. If you do that, 2D minus 1. Same goes for I. Same goes for the formula that we have for the P, for the powers, for the P of terminal, for the P of DC, for the loss, which was 0. So because we are still ideal component. So we have all our average values based on the average of the switching. And this is why we define that duty cycle. The significance that, because you might have a question in last session that why bother to define duty cycle? This is why. Because that now help us to easily calculate the average of those signals. Are we good? Now that we have the average, let's define something else. Again, later on, you would see why we're defining these parameters to simplify more. Instead of having the voltage as VDC times 2D minus 1, let's consider 2D minus 1 as our modulation index. And we call it M. To simplify, less writing, be a little bit lazy. But you are going to see this is not just be lazy. It has a significance. You are going to see later on what is M and what is the significance of M. Okay, so we define modulation index as that 2D minus 1, that multiplication of or the voltage. Okay, and now our terminal voltage is M times VDC. Now, what is our terminal voltage? It was the output of our half bridge. Correct? What is the VDC over 2? The input of our half bridge. So what the significance of M is? A slope is true, but the right terminology would be the gain. Okay, so modulation index in inverters is the gain that you get from the inverters, okay, to changing the level of the voltage, the average level, okay, it's an AC. The average level of the voltage at AC compared to whatever DC voltage that you had in input. Now, anyone can tell me what would be the limitation of M? Like the boundaries of M? What would be the lowest value that M could get and the highest value that M could get? You have the formula here. M is 2D minus 1. Correct? Okay, so what was D? D was the on part of S1. Correct? That was D. So what is the margin of D? It could be 0 top to 1. Correct? So the 0 would give us -1. The 1 would give us 1. So the M could vary between -1 and 1. So gain-wise, the magnitude of M is always less than 1. What that means? That means your average output voltage would never exceed your input DC voltage. Are we good? So whatever average voltage at the inverter you have at the output is always less than the DC voltage, because you are basically, it's intuition wise, you are chopping down that DC voltage. So if you're chopping down, definitely you won't get anything more than what you had. That you are turning off some part of that. The minus plus part is the phase displacement that you create to your signal, which, to be honest, it doesn't matter because we have an AC signal, continuous AC signal. in power system, it won't affect much. It's based on that, we normally, for the limit, we normally only consider the amplitude of M as less than 1. So this is kind of like the significance of that. Are we good? Now that we define the modulation index, we define our voltage and our currents and our powers based on the modulation index. And you can see in the power specifically what would be the efficiency of your inverter. What is the efficiency of the inverter? Any kind of system. The efficiency of any kind of system is output divided by input. Correct? So the efficiency of the gain for the power, the efficiency of your inverters is, in ideal case, is gonna be M. See how significant the modulation index could be? So it defined a lot of things. Are we good? Any questions so far? M the efficiency, what is the power in the batteries is VDC over I, time I, right? So this PDC, this MPDC, this is not the PDCs. This is the DC power in inverter, not the DC power in supply. Do you get what I'm saying? We are gonna clarify that when we go into the non-ideal cases. That makes more sense because I'm separating the supply versus the DC input. Okay. Now, when we had those formula, we could basically create our equivalent circuit, okay, based on the formula that we have as a function of modulation index. This is the same graph that you see before, but instead of those time variant, this is the average model, and we use modulation index as the term that defines the average, which is that 2D minus 1. Are we good? The same model, same kind of like thing, just this is the average model. Now, what happens if our system is not ideal? So far, our system was ideal. No loss, no voltage drop, everything was perfect. But that's not the case in the reality, okay? In reality, in a conducting state, all the switches has a voltage drop. So when the switch is on, the voltage across it is not zero. It has a voltage. Okay? It's small, but it has it. We call it voltage drop. Okay, and we show it here, but we didn't. See here? For all the semiconductor, the diodes, and our switches. Okay? Another one. In blocking a state, okay, we are considering our semiconductors as an open circuit, same as ideal case. Okay? When the switch is on, okay, they would turn on. We consider that turn on. This is also a semi-ideal condition, okay? Turn on instantaneously, but they turn off gradually. In reality, the turn on is also gradual, but it's very faster than turn off. Okay? That's why in like this not even non-ideal case, we don't consider the turn on as any delay. Okay? So second condition, the first condition was the voltage drop. Second condition of the non-ideal was the turn off process in our semiconductors. And the third one is that even when they are turned on, they are not short circuit. they have, where is that? They have a resistance that we could model them. So they have an impedance or resistance, okay, when they are on. So they have loss, basically, what it means. Okay, now, if we input these voltage drop and these resistance into our previous KVL that we run to calculate the voltage of the terminals and the current of positive and current of negative, you remember those? We run a KVL KCL over our ideal model. Okay, if we add these to our ideal model, we are gonna end up with some extra, okay, some extra component in all those KVLs. You know how to run the KVL. I'm not gonna tell you like why is that minus R. It's just a KVL. You can do that by yourself. Okay, so but to show you, you could see here in the graph how they would act as non-ideal condition. Before we didn't have the reverse current. Remember? Before we didn't have the turn off increase. Okay? So running that KVL, including those resistance and voltage drop, which is simple. I encourage you to do that by yourself. Okay? Just add those voltage drop and RI into your already ideal KVL. We could see that our non-ideal voltage, okay, eventually become the ideal part that we had before, the part that represent the voltage drop and the reverse current in the reverse voltage drop in the switches, and a part that represent the loss or like the resistive loss in the switches. Are we good? Any question about that? This is not complicated. I know you see a lot of like integral and like formula here. If you read them, it's very simple. You could follow them. Okay, we just define the voltage drop. We define the resistance based on our formula to simplify the formula, and we have our non-ideal voltage. Are we good? Any question? Go through that mathematics. Do that mathematics by yourself. It is on the PowerPoint, okay? But I encourage you to do that. That makes you understand better, okay? It's the time variant of what's happening in the system. It doesn't matter. You could go over that. Not important. And if you see, if the delay time is very, very low, and if the resistance is very, very kind of like it's close to the R on, we basically go merge to that ideal case. Is the limit. It's not important, to be honest. Just for your information. Now, power-wise. Now that we have non-ideal condition, then our power distribution would change. Now we have some voltage drop, which creates some sort of like a leakage of the current, which represents leakage of the current in our sources. Okay, before negative current and positive current came to play. Do you get what I mean? Before we had a certain amount of voltage that would result in I positive and I negative. Now we cut off, there is a certain level of voltage drop. We lose some of them. So you could represent that as a little bit of a leakage of the current before these two shaped. Are we good? Now, so we have that before our currents are shaped in our switches. We have that resistance, the conducting resistance of the switches that create some power loss, correct? And we have to consider all of them into our power. Now, these are the mathematical formula of how to calculate the power. I'm going to tell you in the graph. The power that comes directly from the DC source, we call it P1. Okay? And we could easily calculate it by the formula. This formula, the derivation of the formula is here. You could follow the derivation in the previous slide. Okay, I'm not going to bother going through that because we don't have much of time. You go through that. P1 is the power directly from the DC source. Now, because of those voltage drop, as I told you, we have a little bit of a leakage. Model them as a leakage. And then we get to our I positive and I negative. So the VDC that goes to the switches is that the PDC that goes to the switches is that P1 minus that leakage. Okay? Now we are entering our inverter. We have a certain amount of like drop in our inverter, and P2 become what we get to the AC part as our output of our inverter. Which again, the derivation is here. You could easily follow that. And now that we have our P1, which is the direct power from the source, and P2, which is the power that we deliver out of our inverter, now we can calculate what we lost between the input and output. And this is not zero anymore because we have a non-ideal condition. Yes.
Is the M as efficiency for this non-ideal case?
No.
Or is that for the ideal?
Ideal. The non-ideal, now you have R and the voltage drop, which do not follow M. They are not function of M. They are characteristics of the switches. Okay, so now the efficiency is different. Now you have to actually divide P2 to P1 to calculate the efficiency. Okay. Same goes for the voltages and currents. Based on the model, you could calculate what is going to be our new non-ideal positive current, negative current, and terminal voltage. Are we good? Any question? No? Okay. So far, we talked about, okay, we have some switches, we create some inverter, okay, and we turn on and off our switches, and something happened. We had our voltage terminal, we have our positive current, negative current, which create our terminal currents. We calculated them, we modeled them, we draw equivalent circuit for them, we introduce the modulation index and duty cycle, and all those things. We talk about the non-ideal condition of what's going to happen, but all the thing that we do, all that model that we do and we developed was started from that S functions that was the function of the time that described the switching state, the on and off state of the switches. Remember that? That was the start of the point, the start of the road that we had all the way through to develop that model. Is that S is going to be as simple as just like DTS for S1 and minus 1 minus D always as S4 or like the bottom switch? No. Why no? Because we need, this is that S switch is the tool we had, is the leverage we had to control our system. Okay, so this is the leverage that we have, that S function, this is the leverage that we have to answer to any fluctuation at the terminal or fix any distortion that we face. So we have to control it. This is our hand, basically. This is our will, that S function. The rest of it, we don't have any control over it. This is a characteristic of the system. The S is our leverage. Now, how we define S, how we control S, there are tons of methodology, tons of, a lot of switching methodology, okay, and techniques. You could search on that. The most popular one that we are going to use in the inverter, and we're only going to focus on that, is PWM, which stands for pulse width modulation. What that means? That means that S function that we talked about, okay, we are going to develop a model or a technique or a function, whatever you want to call it, okay, that by controlling the width of those pulses, that duty cycle, okay, the width of those pulses, okay, we control and we address any challenge or any kind of like variation at our terminal. Make sense? Pulse width modulation. We control the width of those pulses to get what we want. Now, the objective that you want might be control of the load. Simply, like the load increase, you have to increase the power, meaning you have to increase the duty ratio. Simple. Remember, M was the gain. If the point is to reduce distortion, then we have to have different technique to change the pulse width dynamically to reduce the harmonics or eliminate some of them. Okay, we are going to talk about them. Okay, and there are like, or if we have like just simple like fault right through, like there is a fault at the terminal and we have to like deal with that. We use PWM to dynamically change our control and adapt or address to the new situation. Are we good? Now, how the PWM works? The PWM normally works as the control in a duty ratio happens when you define your reference, okay? Define a signal as your reference, meaning this is your desired state. The ideal case that you want to happen at the output. It could be a pure sine. It could be anything, what you want. The ideal case that you want to happen at the output will be your reference, which we call it modulating signals or modulation signals. Okay? Now, what the PWM do is that it would compare these or like have like a reduction like value, like the reference minus a per unit a stable two-wave signal. Okay, so we have a two-wave signal. Okay, we have our desired signal. Here we calculate the reference, the modulation signal minus these two spaces, which we call it carrier. Okay, carrier signal. Okay. Then, if the result is positive, we turn the switch on. If the result is negative, the switch is off for the half bridge. For example, You could see here. When is going to be the result positive? When the reference is more than carrier, right? So here you see the value of the reference is higher the value of the carrier. So the switch is on. And when it goes lower, the switch is off. This is a half bridge, S1. Now, what is S4? Complement of S1. So when S1 is off, S4 is on. Are we good? Does that make sense? This is the very basic, simple case of PWM. No, you won't.
Same media, PWM. The-
True, but it's not everything that
Well,
PWM
just
does.
to put it-
One aspect of that.
That's what-
Yeah. One aspect that it does is that change the average. What was the average of the voltage, the output voltage? Do you remember what was the average of the output voltage was? The VT average? Ideal case. It was M VDC over 2 in half bridge. Correct? Okay. Now, I want you to, I put 2 star, actually, that's a good point. I put the 2 star over there. One over here and one over here. I want to guess what is the significance of that 1 and M on those graphs that I put a start in it. What is the significance of 1? It is a max amplitude. Both of them are max amplitude. Okay, but what is the significance of it? Why 1? Why we don't have a carrier that maximum amplitude is 10 or pi, anything. Normalize it. Yeah, that's true. Why? We are controlling system. We have to normalize our signals so the ratio would not affect the output. The variation now, the amplitude of the variation are not affecting the output. The variation itself affects output. Make sense? The difference between the variation and the amplitude of variation. So we are working in a per unit system. That's the significance of 1. So your reference signal should be per unit. Your carrier should be per unit. Everything is per unit in the control system. In the PWM. Okay? Are we good? Now, what is the significance of M? What M represents in the top graph? That was our modulation index. Correct? And we saw in the formula that we could control the average voltage at the output by modulation index. So by choosing the M, by choosing the level of the reference voltage, okay, if I damp my reference voltage to a less M, so the maximum or like the average is gonna be less. That means I have shorter pulses, meaning I have less average at the output. Make sense? So by the level of the reference voltage, which is M, that I started over there, okay, could define the average voltage at the output. So we control over the gain of our inverter by controlling over how big the reference signal is, the magnitude of the reference signal. Make sense? This is one of the control that we have over with the PWM over our inverter. And as we know, M only could go, the magnitude could go higher than 1, up to 1. So we are still in per unit system. It don't violate our per unit rule. Are we good? Is that clear? Now, when you look at this, we said that the carrier is always have an amplitude of 1. This is our reference signal. Okay, this is one of the parameters. Do you see any other parameters in the PW that could affect the PW? When you look at these signals, one parameter was this reference one. Okay, what is the other thing that could change the switching ratio or cycles or width? What would affect on duty cycle? What would change the duty cycle? Like here, I'll give you a hint. There is two parameters here. Okay, there's two parameters here that would change the width of this pulse. One of those parameters is this reference signal. If I change the reference signal, okay, the duty ratio would change, correct? We talk about that. What is the other part? What is the other parameters? What do you mean?
If switch 1 is high and not.
Okay, that's the result. Okay, that's the result that I'm calling. We want to like change this width, okay, which is our duty cycle. One way is to go higher or lower in the reference signal. That way, we increase or decrease that duty cycle, because the duty cycle is the result of reference minus that carrier. Yeah.
But if
What?
you have the switch on less,
What switch?
that's where it comes.
Forget about the S4. S4 is a complement of S1. Whatever you do for S1 is S4 is determined. Okay? How you could make shorter, what parameters, my question is, what parameters make S1 shorter? What makes it increase or decrease turn on and turn off? Go ahead. Frequency of the carrier signal. Do you see? This is our carrier signal. That's sawtooth. Okay? The amplitude is always 1. Do you follow the
Yeah, because
description?
M is 2D minus 1, which is the switch being on. So that's the modulating signal switch.
You're going backward. I see your point, but you're going backward. Here, yes, we define M as 2D minus 1. Okay? We want to control D, so we are changing M to control D. Okay? In PWM, D is our output, M is our input. We define M based on our reference signal or modulation signal, so we get the D that we want. Okay? Is that clear?
So, right, well, I already had that, because that's what I said, but what is the carrier signal then if the switching is M? Is that VDC over 2?
No. Do not compare. This is not in the power signal. This is in control signal. Both reference signal and carrier signal, it doesn't happen in a power system. The DC source that you have, the switches, are in a power circuit. We have a control circuit, okay? It's a way that we control our power circuit.
So it's just the carrier signal, it's just.
It is a carrier signal. It's
frequency.
there is no natural frequency here. We have a carrier signal, is a sawtooth. The amplitude is always 1. Okay. We compare that with the reference that we desire, and that comparison would create the signal on and off for the switches, for the gate of the switches.
So then the S1 frequency.
The frequency that your friend talked, okay, that's it, is the frequency, where is that? The frequency of PWM pulses, okay, which is the frequency of our carrier.
It is, okay. That's
Okay.
what I was-
If I increase the carrier frequency, that means we have a sharper carrier signal. Okay, then we have different switching at the output. Make sense? So 2 parameters in PWM changes the output. 1, your reference signal, which is basically your modulation index. Okay, what you want. 2, your frequency of your carrier signal. These two, by playing with these two, you could change the output signal that switches on and off, that turn on and off the switches. Is that clear? Are we all good? Any question? No? Now, that is the ideal case. The non-ideal case is that, okay, we have a deviation in a desired output. Always we have. Okay, we have uncertainties. And we have delays. Okay, we have delay. We said that it is not like we turn off the switch and it turn off instantaneously. Remember that? So that means it doesn't matter how accurate your PWM is, the reality has a little bit of deviation. Okay, so there is going to be a delay on turn on and turn off when you want to do actual. See, this is the ideal case. For example, that you switched on and on. This is what's actually happening. There is a delay in turn off and turn on. And also, if you look closely here, even in the conducting mode, there is a voltage drop. The voltage is not 0. It has a value. So these are the 9 ideal cases. How we could deal with them? We have to use more advanced technique than just the two, like a reference minus carrier. There's more advanced techniques to create that output signal. Second, we have to make it dynamic. So the reference signal would change based on the output that you get. It's like a feedback. So we have to have a dynamic PWM. We say, okay, this is like a try and error thing. Okay, we define the desired voltage, we give it to the PWM, it switches on and off, we measure what happened, we see there is a deviation, we try to fix it. Again, happen, still deviation, try to fix it. You can search the terminology of Newton-Raphson control system, Newton-Raphson regression or Newton-Raphson control system, feedback control loop. This is the baseline of that try and error kind of like method. Okay. Now, there are several types of PWM. One is unipolar PWM, what you see so far. That was unipolar PWM. Okay, a simple one. We could have bipolar PWM. The difference between unipolar and bipolar is the same difference as half bridge and full bridge. instead of one signal that describes, that runs both S1 and S4, you have two signals. So now you have more control. You have less uncertainty. Okay, you don't need to worry about that. That bipolar would not normally use in our system. I'm going to talk about the most important ones in single phase and in three phase. In single phase, the most important part is SPWM, sinusoidal PWM. This is the system that the reference frequency, the reference signal is always a sinusoidal value. What you change is the magnitude, frequency, and phase of that sinusoidal voltage. So you have the three parameters in a certain sinusoidal function: magnitude, frequency, and phase, initial phase. Okay, you change those three in order to control your reference. So in SPWM, we can't just put in any arbitrary reference signal. It's always a sinusoidal, but you can play dynamically with the amplitude, frequency, and phase. Are we good? SVM, the space vector PWM, is for three-phase system. We are going to see what is happening is the whole like is based on the state space theory. You know the Euler's formula and Laplace transform. I assume you heard about that. Okay, but it doesn't matter. It's very easy. If you didn't hear that, it's you don't need to like worry about it. It's very easy. Okay, the concept that you need. So the space vector is for three phase, normally used for three phase. It is better to use for three phase. SPWM is most popular in a single phase. Okay. As we said, SPWM, we have a sinusoidal voltage that we can play with the phase and amplitude. So what happens is that always, as you can see, our switches, the on and off portion of our switches basically mimics a sinusoidal. The turn on is, the duty ratio is low and goes higher when we get to the 90 degree, and then goes lower and then reverse in the negative half cycle. You see the pulse width follows the sinusoidal variation, that duty ratio. And you could see here, this is the difference between the unipolar and bipolar. In bipolar, you have two signals, you mix them, and you have sharper PWM. Okay, this is kind of like the difference. You don't need to worry about that. Okay, it's not that hard. It's just like instead of one PWM, you have two sets of PWM, and then you have mixed them up, and you get what you want. Okay, so this is SPWM, very useful, and it gets more beautiful when we add it to a multi-level. Now, in multi-level inverter, remember, we have a bunch of cascaded inverters, full bridge or half bridge, doesn't matter, okay, that overall create the whole signal. Now that the whole signal should be divided between the several modules in our inverters, that per unit part that we talked about, we have to normalize it again. Each carrier, you see each carrier here represents or answers to one of the modules. Each color actually, like no, not color. It's these two is for one H bridge. These two is for another module. These two for another module, and these two for another module. Are we good? Positive and negative of one module. Each module is a separate inverter. But because cascading them creates our desired sinusoidal, the carrier should be add up to 1. Each of them now is not 1 anymore. For example, here we have 1, 2, 3, 4 modules of inverters, okay, cascading each other. So each of the carriers is 0.25 amplitude if our reference is per unit. Are we good? Does that make sense? Now, consider this, what's going to happen in a multi-level inverters. We have cascading. Each level uses that PWM to create pulse width. This is a simple pulse. Consider if it's a high frequency PWM, all of these are a series of pulses that mimic a sinusoidal. Okay? And it would create basically a perfect output voltage very close to the ideal sinusoidal that we want. Make sense? Is that clear? Now, what is the significance of this SPWM? Why is popular? Especially when we're dealing with multi-level inverter. It's modeling, because we're talking about the control tool. It's a control tool, so it's not modeling anything. It is our leverage to control what's happening in our system. You know what I'm saying? The SPWM is your hand that doing the stuff, doing the changes. It's not modeling what's happening. It's changing the situation. It's the leverage, the input.
I mean, whenever I say that, I mean, this is all how to model what we want to do in real life. I don't know. Because this is just setting up like the tools that we're going to use to put into our designs.
Yeah, that on that perspective, yes. Yeah, on that perspective, yes. Now, what is the significance of that? What is the use of that? We said we can represent our voltage of output based on the Fourier series, correct? So this voltage as a Fourier series, you could Google it and you'll find that someone already did the math. You don't need to like worry about this y is 4 over n pi. Someone did it. You just have to like use it. Okay. So we have a Fourier series here. Okay. When we have multiple levels, we have multiple factors or degree of freedom. We have more variables. We have more degree of freedom to control our output. Make sense? We have more leverage to control our output. So now, instead of like just haphazardly try to reduce the harmonics, we could focus on very significant one and aim to eliminate them. For example, here, one case is to like eliminate the third harmonic, the fifth harmonic, okay, or like the seventh harmonic. These are like if you search that, these are the most significant harmonic that inverters inject in the system. And you calculate, you run the code, you calculate what should be my frequency and my phases of my reference signals that go to the PWM, how I could decide about these theta's, the time that each level gets on and off, okay, in a way that I could make these harmonics equal to 0. And my main component, the voltage that I want. It's a simple optimization code. You write a code, you say, okay, try and error. If I choose theta as like 1 radian and theta 2 as like 1.1 and theta 3 as like 1.7, do I eliminate these voltages and keep my main component as much as I want? Your computer, your MATLAB M file would run and say, okay, this is going to be the result of that configuration of theta's. Now you say, okay, change the theta's, tell me what's happened. It would sweep all the options and gives you the best option that reduces those harmonics to 0 and keep your fundamental as what you want. Now you have the optimal situation and you could have the best signal that you want at the output. Make sense? This is the way of generally it works. Now, a space vector that we said is in this three-phase system is based on the Euler formula. Okay. Euler formula, we defined e to the power of j2 pi over 3, which is 120 phase shift. Okay. E to the power of j2 pi over 3 is 120 degree phase shift in one cycle of sinusoidal. So in three phase, we know that we have three voltages that they are shifted 120 volt from each other. So if the voltage A has 0 theta, theta equal to 0, theta A is equal to 0, phase B is minus 120, phase C is plus 120. 120 phase shift from each other. Make sense? We have three phases. So how we could describe that? We could say that, okay, voltage, we could say that the voltage A is VA, voltage B is A times VA, and voltage C is A squared times VA. Makes sense? 120 phase shift, 220 phase shift. Make sense? This. Sorry?
So 120, the other one is 240.
2 times 120, 240. Okay, so yeah. And we already know, because we're dealing with inverters, we already know that our voltages are the S function that we had times the DC voltage. We had that formula before. You remember that? Okay, now we implement all this definition to a output voltage of our three phase. What happens is that we would have a voltage that is 2/3 of the DC voltage, okay, times now those phase shift, instead of applying them to the voltages, we apply them to the S signals. Is that clear how we reach that? Now we have three S function with 120 phase shift with each other. Make sense? Is that clear for everyone? Now, if we decide on S function, let's say we say S of A, we define the sectors of a space, like from time 1, from time 0 to T1, we call it a state 0. From T1 to T2, we call it state 1. Okay, we section our time. one cycle, okay? Or like half a cycle. We section it in a different state. For each state, we define the optimum value, okay, for S A, S B, and S C. Okay? And based on the formula that we develop, we would find the result of the space function, how they would add up together. And that would result in our output voltage. Is that clear? I know it's a little bit kind of like shady, but you have to like review that multiple times to like get to that. No, but it's very clever method. It's one of the most intellectual kind of like method for the PWM. Okay, it's very intellectual. So when you do this setting for SA, SB, and SC, and you do all the math and all the phase shifted, you will get the vectors that shapes your output voltage. If you wanted to like draw it, it's gonna be VA, VB, VC based on what we said. These are the states, V0, V1, V2, like for example, okay? You see S1 is on V1, V2, and V7. See? Okay? Oh. And then if you add these three together, what you would have? You would have your PWM multi-level signals as the inverters at the output. Or in three-phase, basically, in three-phase, voltage of the line, this is voltage phase A, phase B, phase C. So the line voltage A, B become the addition of these two vectors. AC become the addition of these two, and BC the addition of these two. You could see how it would reduce the harmonic. Is it clear how it would affect to get more closer to the ideal case? Okay, I'm sorry, I'm again past a little bit over the time. I'm gonna stop here. Basically, it's done. It's the discussion is done. Keep following the Canvas page and let me know if you have any question. Thank you very much.